Okay, welcome everybody. Today we have Jan Wiersig from the University of Magdeburg, and he will be talking about quantifying the response of open systems at exceptional points. So when you're ready, Jan, go ahead.
Yeah. Okay, now can you see the laser pointer here?
Yeah, we see a pointer. It's not a laser pointer, but
yeah, but
it's
a kind of
an arrow.
of it. Yeah. You can't see this small red light, but you can see the arrow. You can see.
We see the arrow. Yes.
Okay, perfect. Okay, yeah. Thank you very much for this introduction, also for the invitation to the seminar. In my talk, I speak about exceptional points in open systems and how to quantify the response of these systems at the exceptional points. A short outline of the talk is given here, so I will give a brief introduction to exceptional points and also to optical microcavities. I will then ask the question of how strong an exceptional point is. Then I will discuss something which seems to be completely unrelated at first, namely the distance of a given exceptional point to the set of diabolic points, but we will see that this is related to the other questions. And then I will give a summary. So let me now. No, I cannot switch to the next slide. Oh. Okay.
Try just using a down arrow.
Yes, this is what I've done. No, I can't use this. No. No, I cannot. Strangely, this has not happened before. We cannot change the slide. What can we do?
Difficult to say. The problem is on your side, really.
No, I can. Okay. It has something to do with the spotlight, with the laser pointer, which doesn't work anyway. Okay, so now I have. Do you see here some remainings of my drawings?
Yes,
not a problem,
we do.
I think. Okay. Okay, let's come to the introduction first. So let me start with briefly explaining what an optical microcavity is. This is the one, or the objects that we study in our group. So maybe a prominent example is such a micro disk cavity. Yeah, there you can confine light on a micro scale just by total internal reflection. Yeah, as in this cartoon for this ray here, you have total internal reflection. But actually, it turns out that at a curved interface, total internal reflection is not total, but there is some decay to the outside, some tunneling, if you want, like you would call it in quantum mechanics. Now, the corresponding wave solutions of Maxwell equations, that are the optical modes. Yeah, they correspond to the energy eigenstates, that are the states which have a harmonic time dependence. Yeah, can be decaying, of course, but it's harmonic time dependence. In this kind of geometry, these modes are called whispering gallery modes. Yeah, this name comes, for instance, from the St. Paul's Cathedral in London. There's the whispering gallery. You stay there somehow. I hope you can see the people here. So if you then whisper and the sound goes then to the wall, it travels along the boundary, like this light ray here or this electromagnetic wave. Yeah. So these are these whispering gallery modes. And they have this also the quasi-bound states, if you want, or correspond to the energy eigenstates of the quantum system. They have a resonant frequency, omega, and they have a lifetime tau. Yeah, and usually in optics, people like to express it with the quality factor. It's a dimensionless number, and it's a product of frequency and lifetime. And these microcavities are studied in various different fields. They have many potential applications, for instance, in microlasers. Yeah, they play the role of a laser resonator. Yeah, you want to keep the photons as long as possible in the gain medium, such that the photons can contribute to stimulated emission. Other applications are single photon sources, filters, sensors, low power parametric processes like like down conversion, or cavity-led optomechanics. Here are some other examples. There are also cavities with whispering gallery modes, microspheres, so here the light travels here along this boundary, or microtoroids, can imagine that the light travels here around the boundary. And just for completeness, there are also other cavities which exploit photonic band gap, which is not important for our talk. So we focus on these whispering gallery cavities. And now let me mention what we're doing in my group. So almost everything is somehow related to optical microcavities. And roughly half of the people are studying semiconductor nanostructures which are embedded in these microcavities. Yeah, for instance, semiconductor quantum dots. Yeah, you can place them in these microcavities and then you can study light matter interaction. Yeah, for instance, then we look at many particle quantum physics, photon statistics, mainly in microlasers. We look at collective effects such as superradiance or mode competition. And recently also we had a look at the maximum entropy method to study these many particle quantum physics. The other half of the people is doing what I may call complex wave phenomena in microdisk cavities. So for instance, we study what happens if you deform such a microdisk cavity. Yeah, this is interesting because there's an interesting ray wave or classical quantum correspondence, if you want. There's also, from the application side, it's interesting because you can achieve directed emission. Yeah, you can see this here in the inset. And from a theoretical point of view, we're interested in weak boundary deformations because there's an interesting perturbation theory around for this. And of course, non-Hermitian optics, photonics. And this is what I mainly speak about today. And we will also just briefly touch this weak boundary deformations. Okay. Now, non-Hermitian phenomena, exceptional points. I think I don't have in this audience to say so much about it, but just let us go briefly through it. So we all know that open wave and quantum systems, they are the mode frequencies or the energy eigenvalues. They are complex valued. Yeah? The imaginary part determines the lifetime of the state. The modes or the energy eigenstates, they are in general non-orthogonal and they may not form a basis. Yeah, and this happens at exceptional points. Non-exceptional point is a point in parameter space at which two or more eigenvalues and eigenstates of a non-Hermitian linear operator coalesce. And let me just mention that it's not enough that the operator is non-Hermitian, it has to be non-normal. Let me also mention that I do not distinguish here really between Pt symmetric systems and non-Hermitian systems. Yeah. So as Michael Berry once said, NH is the big brother of Pt. So it's a more general if you want. Now, let me mention this exceptional point is very different from a conventional degeneracy where only the eigenvalues coalesce. Now, the eigenstates can always choose to be orthogonal. And one other difference between this conventional degeneracy, which is also called diabolic point, and an exceptional point, is that when we perturb the system or when we vary to or more parameters, then we see a root behavior, yeah, at the exceptional point. So here are shown the eigenvalues, the absolute value, such that I only have to show one graph and not two, as function of two parameters. Here we have in the case of an exceptional point of order 2, so an exceptional point where exactly two eigenstates coalesce, we have a square root behavior, whereas for a diabolic point, we have a linear behavior. Yeah? And for exceptional points of higher orders, for instance, exceptional point of order 3, where exactly 3 eigenstates coalesce, we have a cubic root, and so on. Now, there have been, meanwhile, many experiments on this. I mean, almost countless, I would say. So this has also been proven to be relevant for physics, physical systems. And let me just show one example. Consider such a whispering gallery cavity. Yeah, let's say a microdisk. Yeah, and such a microdisk in a two-mode approximation, you can say we have one mode going clockwise, one mode going counterclockwise, and we can describe this with two complex numbers, A, CW and A, CCW. Now we perturb the system, yeah, breaking all the symmetries, making the system also non-Hermitian. It was non-Hermitian before, of course we have option losses before, but now break all the symmetries. This you can do in practice by, for instance, by using 2 nanofiber tips. Yeah, this is shown here. Or you can also do it in some sense by arranging a Pt symmetric arrangement of gain and loss on such a micro ring. Or you can take such a micro ring and include some these asymmetric S-shaped inner structure here. All of them, what all of these geometries introduce is the asymmetry between the scattering of clockwise and counterclockwise waves. In an extreme case, we can achieve such a situation. So this is the differential equation for these amplitudes for clockwise and counterclockwise propagating waves. And we can always write us down in the kind of Schrödinger-like equation with an effective Hamiltonian. And if we choose everything right, we can achieve a situation where here is a zero, meaning that there is a scattering from clockwise to counterclockwise propagating waves, but not the other way around. Yeah, clearly this Hamiltonian is an exceptional point, right? The only eigenvector you can find is this, which corresponds here to a purely counterclockwise propagating waves, shown, for the example, is shown here. Yeah, these are full calculations. This is not, of course, just a two-mode approximation. Yeah, so we have this kind of chirality, which is inherent for all exceptional points. Here, this chirality turns into a chirality in real space for this particular kind of systems. Okay. Now, since it has been proven that exceptional points exist in physical systems, now people started already 2014, 2016 to look for applications. Yeah, and there are some ideas around. This is not a complete list, of course. Asymmetric light transport, orbital angular momentum lasing, optical amplifiers, and exceptional point-based sensors. And the idea there is that you take advantage of the square root behavior of the energy eigenvalues, or here the frequencies, when you perturb the system. Yeah, here's the perturbation parameter. You perturb the system. You see for an exceptional point, you see a square root behavior on EP of second order. And for the DP, for the diabolic point, you see a linear behavior. And for small enough perturbations, the square root always wins, right? It's always larger. So you see a larger splitting for exactly the same perturbation. And this can be used for sensing. So here's one of the first experiments showing this effect. So you have a microtoroid here. You implement an exceptional point by using 2 nanofiber tips. I hope you can see this here. And then you use a third nanofiber tip to simulate a target particle that you want to detect. So imagine you have your microtoroid and you want to detect some, let's say, a coronavirus, for instance. Yeah, you can do this, for instance, also by functionalizing the surface of your resonator. You make it only certain types of molecules detect. And now in this particular case, you can compare a diabolic point and an exceptional point. The diabolic point you get very easily in the perfect microtoroid. Clockwise and counterclockwise propagating waves actually are at a diabolic point. Now with the nanofiber tips here, you can implement an EP, and you see the splitting is larger for exactly the same perturbation. Yeah, it's about a factor of 2.5, so it's not really impressive. But there have been also experiments using a third order exceptional point. So there, the cubic root gives even a larger splitting. And there, the enhancement factor of the splitting has been 23. Yeah, so it's really quite a big effect. Now, I would like to ask the question, how strong an exceptional point is. So we have just discussed that an exceptional point is somehow stronger than a diabolic point, meaning that this frequency splitting or energy splitting at an exceptional point is stronger than at a diabolic point, yeah, for small perturbations. Now we would like to ask the question, what if we compare two exceptional points? Yeah, let's say of the same order. Yeah, both show a square root behavior in second order, but one can have, of course, a larger prefactor. Yeah, so can we now somehow quantify this? What we, of course, always can do is we take our two exceptional points, we add the perturbation here called epsilon times h1, calculate the eigenvalues, and then compare the eigenvalues. Of course, this is trivial. Yeah. But I would like to ask, can we do this somehow, in some sense, simpler and more general? Can we really assign a single number, independent of the perturbation, for a generic perturbation, for typical perturbation? Okay, and the answer is yes, we can. And for this, it's useful to look at matrix norms. So it's clear to me that physicists usually are not familiar with metric norms. Mathematicians are. So let me just explain it very briefly. So usually what physicists are familiar with are vector 2 norms, right? So it's just the conventional vector norm that you use in quantum mechanics, for instance, right? Now a matrix norm now can be defined with these 4 axioms. Yeah, so it's a mapping like the vector 2 norm, that is a mapping of the vector to the non-negative real numbers. A matrix norm is a mapping of a matrix to non-negative real numbers. Yeah, there are certain properties, for instance, here this triangle inequality, which tells you that the matrix norm of a sum of 2 matrices is smaller or equal than the sum of the norms of the individual matrices. Now we have also this inhomogeneous, absolutely homogeneous property, the definite property, and what is not known from these vector norms is this submultiplicativity, saying that the norm of the product of 2 operators is smaller than the product of the norm of the 2 operators, the individual operators, right? And using these norms, I forgot, they are usually people consider 2 additional properties which are not in the definition of the metric norms itself, but very useful, and many norms fulfill these 2 properties. The first one is the Unitarian Invariance. Yeah, so meaning that if you have unitary matrices U and V, this condition holds here. And then there's the compatibility with the vector 2 norm, meaning that when you have the matrix A applied to a vector psi, and there the vector norm, this is smaller than the norm of the matrix A times the norm of the vector. So 2 very popular norms which fulfill all of these properties are the Frobenius norm and the spectral norm. The Frobenius norm is here calculated with the trace of A dagger A, and easy calculation shows that if you have a matrix representation of your operator A, then it's just very natural generalization of the matrix, so of the vector 2 norm, right? This is the most naive thing you would write down. Slightly more fancy is the spectral norm, which is defined, for instance, in this way, when you say it's you apply A to arbitrary unit vector psi, and then the maximum of this gives you the spectral norm. It's exactly then if you would define it with being the largest singular value of A is the same. Okay, the unique feature of the spectral norm is that it's the smallest norm that is compatible with the vector 2 norm. Yeah? In particular, it means that the spectral norm of an operator A is smaller or equal than the Frobenius norm of the same operator. And the equality holds for rank 1 matrices. Okay. Okay, now with this short review of matrix norms, let's start. So we start with the eigenvalue equation of our perturbed Hamiltonian, right? We assume that the perturbation parameter is non-negative without loss of generality. Then we put the right term here to the left and the perturbation term to the right. Right? It looks like this. And then we take the inverse of this matrix here. Let me just mention that I always think about finite sized matrices, right? So all the problems that you might have with infinite dimensions, I ignore here. So we take the inverse of this. This is nothing else than the green function or the resolvent. Yeah. Yeah. So we have a formal solution for this, and then what you do is you take the vector norm on both sides, and assume that your eigenvector is normalized to 1. Then you get this expression here. And then we use the compatibility to the vector 2 norm twice. Yeah, so we get this expression here. Let me mention that I always write a matrix norm in blue and the vector norm in red. This helps a little bit to see it better here. And then finally, I use the fact that the eigenvector should be normalized to 1. So then we get this equation or inequality, sorry, this inequality here. Okay, we take this inequality and then we specify our Hamiltonian to be n times n. And this Hamiltonian should have an exceptional point of order n. Yeah, that's the simplest scenario, let's say. Yeah? And then it's known, yeah, already since Cato, but it has been reinvented at least once by Heiss, that the Green's function can be at the exception point, can be written in this way, where capital N is the traceless part of the Hamiltonian. It has the special property that it's nilpotent of index n, meaning that n to the power of n, capital N to the power of small n, is 0, but n to the power of n minus 1 is not. Yeah. Now what we do is we assume that our energy eigenvalues, so here in the Green's function here, the energy eigenvalues of the perturbed system enter. We assume that the perturbation is weak, so that our eigenvalues are still nearby, also close to the energy eigenvalue of the exceptional point. So then we can restrict ourselves to the leading order term, so that one, the last one, to highest order. Yeah, we plug this in, we multiply here by I minus I EP to the power of n, we get this expression. And this is now an inequality that gives an upper bound for the splitting induced by the perturbation. Or maybe it's better to say it's not the splitting, but it's the change of the eigenvalues. Oh, here's the J missing. It's the change of the eigenvalues with respect to the EP eigenvalue. And important, on the right-hand side, there's a product of two factors. One depends only on the perturbation, and one depends only on the exceptional point.
Philip has a question. Sorry, Jan,
yeah.
there's a question.
Yeah,
it's just a very general question.
yeah.
If I just give you an arbitrary Hamiltonian H0,
Yeah.
and it has an exceptional point, is it guaranteed that the resolvent exists, this G of E?
Yes, for let's say for finite dimensions.
It certainly exists if there's no exceptional point.
Say again.
It certainly exists if there's no exceptional point. But why is it? It's not obvious to me that it would exist if there is an exceptional point, because you don't have a complete set of eigenvectors.
Say again.
You don't have a complete set of eigenvectors.
Ah, yeah, this is no problem. You see, the eigenvectors are not here. It's you can also write the Green's function in terms of the eigenvectors and the Jordan vectors. There is a recent paper by Rami Al-Ghanani,
Yes,
and Shahin Özdemir who have done this. But here, there's no need here for the eigenvectors.
Oh, you're saying that nonetheless you could write G of E in terms of an incomplete set of eigenvectors.
Yes.
Ah, okay, thank you.
This is the formula for it. Yeah, you can look at it in Cato already, and it has been discussed there. Okay, now what we do now is we restrict ourselves to this.
I'm sorry, I take that back.
Yeah.
From the eigenvalue equation,
Yes.
I can't tell that I have an exceptional point. I've just got an nth order polynomial expression and it has n solutions. But that doesn't mean that every one of them has an eigenvector. So constructing G of E from the eigenvalues does not guarantee that the function exists if there's an exceptional point. That's my question.
Okay. I'm still not sure if I fully understood it, but let me just first say that when I speak here about eigenvectors, I mean the eigenvectors of the perturbed system. So we are no longer at the exceptional point, right? So our H0 is at the exceptional point. This eigenvalue equation is not at the exceptional point. It's somehow perturbed Hamiltonian. And so, I mean, this equation is this the Green's function.
Oh, I see. So what you're doing is something else. What you're saying is, let me perturb an exceptional point Hamiltonian so that the perturbed Hamiltonian doesn't have an exceptional point.
Yes. So the psi j vector are eigenvectors of an Hamiltonian no longer at an exceptional point because we have the perturbation epsilon h1.
Okay. Yes. So my concern was only if the perturbation left the full Hamiltonian with an exceptional point.
Now I understand your point.
Okay,
okay.
thank you.
Yeah, okay. This is of course a good question because I didn't say much. Of course, I said we take the leading order term, right? But there's one subtle thing to it. I just didn't mention it. Of course, if I see here, the Green's function is multiplied by a vector. The vector is h1 times the vector psi j. If, of course, by chance, this vector here is a special vector that gives 0 applied to the leading order term, then, of course, my argument breaks down. So I have to assume, it's mentioned in my paper, but not here in the transparencies, that h1 times this vector here multiplied with this leading order term does not give 0. So this is a non-generic case, and one has to include this. This I agree. But apart from this is the general expression for the Green's function at an exceptional point of order n. And I can recommend my appendix, my paper. There's a very simple deviation of this. It's a few lines. It's not very complicated. Nothing special behind this. Okay, now I continue here. Now I want to restrict ourselves, or we want to specify now the matrix norm to be the spectral norm, because the spectral norm is the smallest, right? As I mentioned. So it gives the best bound. Yeah. So I want to have the best bound possible here on the right hand side. Yeah. So that means I write here 2, and this spectral norm of this n to the power of n minus 1, this I call psi. I call it the spectral response strength, yeah, of a system at an exceptional point of order n. So it can be easily calculated as the power of n to the power of n minus 1, and then the spectral norm. One funny thing is that you can also use the Frobenius norm here, simply because the matrix n to the power of n minus 1 is of rank 1. And in this particular case, in this very special case, the Frobenius norm gives the same value. But here, for h1, I have to take the spectrum. Right? Let me also mention that in mathematical literature, there is already concept like this already exists already. It's called the Hölder condition number. I would say that in principle it's the same. Here, my derivation, I would say it's simpler and more for physicists maybe, because what is good is that the Green's function is needed also in other places, so it's very good to do everything with the Green's function. Okay. So now let me just summarize this point. So important equation is here. So the splitting or the change of the eigenvalues with respect to the original eigenvalue at the exceptional point to the power of n, absolute value, is bounded from above by this expression. One factor depends only on the perturbation, one only on the exceptional point. Yeah, and we can calculate this easily, right? It's very easy to calculate. Yeah, so we can now say, give me an exceptional point. I can tell you how strong this exceptional point is. And with strong, I mean the spectral response in terms of the splitting of the eigenvalues, of the change of the eigenvalues. Now, it turns out that this psi turns up also in other situations, for instance, in this one. So imagine you have, let's say, for concreteness, you have such a Pct symmetric system here, Pct Symmetric Trimer, so we have here gain, here loss, neutral one, yeah, so you have the same amount of gain than the amount of loss. And now you want to excite the system, for instance, by using waveguide, and you want to measure what is the steady state intensity somewhere, let's say here, then you can just put another waveguide and then you can measure the intensity. Now, mathematically, it means you have to solve such a inhomogeneous Schrödinger-like equation, yeah? So omega is the excitation frequency, capital P is the pump strength, and the small p vector is here the excitation, the generic, let's say, excitation pattern or vector. Yeah? If you do the calculation, and I don't go through the details, just the result, it turns out that the steady state intensity response to excitations looks like this. So on the left-hand side is the total intensity or probability in the quantum context. In the optical context, it's the intensity, and it's bounded by this expression here. So the pump strengths appear. It appears a Lorentzian line shape to the power of n. Yeah, if it's if n is equal 1, then you get just a conventional Lorentzian. Also for a diabolic point, it's known that you get a Lorentzian. It's known that for exceptional points, you get something complicated, more complicated. For instance, for a second order exceptional point, you get a Lorentzian squared, and so on. Now, this comes out in this equation. I mean, it's not new, so to say, but it comes out very easily. But what is new is that these psi appear here. At the same psi than before. So it means when the quantum dot, sorry, the exceptional point is strong in the sense of a strong spectral response. It is also strong in terms of intensity response to excitations. Okay. So let me now briefly mention passive systems. So physically, you would say that are systems where there is no gain. Yeah? Mathematically, you might say the decay operator is positive semi-definite. Now, if you use this property, and I jump over all the calculations here, you can do for n equal to a calculation which showing that this response strength is bounded from above by this expression here, by 2 times the absolute value of the imaginary part of the exceptional point eigenvalue, which is nothing else than the line width that shows up in the spectrum. I call it here gamma. Now it's clear if you want to resolve the splitting experimentally, the splitting should be larger than the line width. So now it turns out that for passive systems, these things are related. So if I have a large splitting, then I can have a large, if I have a large line width, I can have a large splitting, which I actually also need to resolve it. But if I have a small line width, which helps me to resolve the peak, I have only a small maximum splitting, right? So this is counteracting this, yeah? So these conditions here for passive systems are really a restriction for passive systems. And it means that in experiments to see very big splitting or splitting much larger than the line width, you either have to use strong perturbations or you have to gain. Yeah? Strong perturbations in the context of sensor you don't want to use, right? Then that means you have to use gain. You can do the calculation also for n equals 3, so third order exceptional point. There's also a bound for the spectral response strength. It's given by a different formula. In both cases, let me mention that you get the inequality here and here if the decay operator is of rank 1. That means if it's a single channel loss system. Yeah. Okay. Okay, now we have spoken about eigenvalues. Now what about eigenvectors? You can ask this a similar question. So what is the change of the eigenvectors orthogonal to the eigenvector, to the single eigenvector of the exceptional point? Now people have done calculations like this, and they've seen how the Jordan vectors appear. I want to do the same calculations also with an inequality, giving us a number that we can associate to the exceptional point. So this number I call the eigenstate response strength. You see it's a bit more complicated. The psi also appear, but a more complicated expression here appear where the Jordan vectors appear. The Jordan vectors, I don't want to go into much details here. If you don't, I'm sure most of you know, the Jordan vectors are kind of generalized eigenvectors, which gives you a basis for the generalized eigenspace of the exceptional point. They're actually not necessarily orthogonal, but they are linear independent. And what turns out that you need the first Jordan vector, which is nothing else than the eigenvector of the exceptional point, and the second one. And this expression itself is not so important. Important is how it then enters. So here on the left-hand side is very similar than what we have seen with the splitting. On the left-hand side, you have the change of the eigenvector, the vector norm to the power of n, is bounded from above by a product of 2 factors. One, again, only depends on the perturbation. That's the same as we had before. And then we have another one which depends only on the exceptional point. Yeah, we call it zeta. And zeta and psi are in general independent quantities that characterize the exceptional point. But I forgot to mention, maybe if you're familiar with quantum metric approach, it has some similarities to it, but it's different. In particular, here with with using the inequality here, we can separate the perturbation and the influence of the exceptional point. This is not done in this quantum metric approach, but there are some similarities. Okay, now I want to continue my previous sentence. In general, psi and theta are independent quantities, but for the special case of an exceptional point of order 2, they are simply related by this. Yeah, so theta is just 1 over psi. And this means that if you have an exceptional point with a large spectral response strength, it necessarily has a weak eigenstates response strength. Yeah, that means this is a kind of robustness. Yeah, so your eigenstate is more robust the eigenstate of this exceptional point, if the zeta is small, is more robust than eigenstate of an exceptional point with a larger zeta. Yeah, so it's a kind of robustness of the eigenstates. Yeah, I think this has not been discussed in the context of the exceptional points, but maybe you know something. Okay, now let us come to examples. So I mentioned already these whispering gallery microcavities with fully asymmetric backscatter. Yeah, so here we have effective Hamiltonian looks like this. I forgot to mention that this omega are the frequencies and A is the backscattering coefficient. And if you do the calculations, I mean, for 2 by 2 matrix, it's very easy. Yeah? You find that this psi, the spectral response strength, is just the absolute value of A. Yeah, it's very intuitive result actually. And that means when you want to increase the spectral response strength of your exceptional point, you have to increase this internal backscatter. Yeah. If the system is passive, and usually it is, we can calculate these upper bound for the spectral response strength. It looks like this. If we put on the right, this here on the left-hand side, we get this inequality, and this is actually something known. Yeah, for this particular kind of system, it was known that A, the absolute value of A, is bounded from above by this expression here for passive systems. Now, this zeta is, I mean, just by the simple relation that zeta is 1 over psi for an exceptional point of order 2, zeta is just 1 over the absolute value of A. So it means if I have a large backscattering coefficient, then the change of the eigenvectors will be small. This stabilizes the mode in a sense. Yeah? And I'm quite sure this has already been used unknowingly in this experience with the orbital angular momentum laser. So they rely on the fact that the mode has a 100% chirality, or at least close to 100%, meaning that it goes only counterclockwise or clockwise. And of course, you have fabrication imperfections, so you're not at the exceptional point and stuff like this. Now, it turns out if the backscattering coefficient is large, then this is no problem. Then you still have a nearly 100% chirality state. Here's another example. This is the Pct Symmetric Trimer. Here's the Hamiltonian, omega 0 is the frequency, alpha the gain loss contrast. So here's gain, here's equal amount of loss, here it's neutral, G is the coupling strength, and you know, of course, that we get an exceptional point of order 3 when alpha is fine-tuned to square root of 2 times G. And now we plug this Hamiltonian and the eigenvalue here into our formulas, and we get that the spectral response strength psi is 2 times alpha squared. That means if you want to enhance the spectral response strength here, you have to increase the gain loss contrast. At the same time, of course, it has also to increase the coupling strength, yeah, because you want to stay at the exceptional point, of course. And the eigenstate response strength now cannot calculate it with just using 1 over psi. You have to do it once again, the calculation, and you find it's 1 over square root of 2 times alpha. And also here, if you increase the gain loss contrast, you reduce here now the eigenstate response strength, thereby making the state more robust. Perturbations. Okay, next example is random exceptional points. What I mean with random exceptional points, I mean that I take an ensemble of Hamiltonians at an exceptional point of order n with eigenvalue EEP. Yeah, I fix n and EEP, and then I generate a large amount of realizations of Hamiltonians by using this expression here. J is a n times n matrix in Jordan normal form, with the eigenvalue EEP. Q is a general non-unitary n times n random matrix. And if I do this calculation here, my H0 will be at an exceptional point of order n with the correct eigenvalue. H1, so the perturbation is just an n times n random matrix. And if I do the calculations for this quantity, this is a kind of dimensionless spectral response. So I take x to be the ratio of the maximum of the eigenvalue change and divide it by this expression here. And according to our inequality here, this quantity should be between 0 and 1, right? And if I do the numerics, I found for the probability density function of this quantity x, I found this histogram here. I'm using 10 to the power of 7 realizations. And you see that, first of all, it does not go above 1. Yeah. So there's one question I see.
Yes, I have a little question. Did you try to relate your calculations to the well-known technique of pseudospectral approaches? Because it looks very much your resolvent techniques and all this. It looks like a kind of inverse pseudo-spectral technique, in a certain sense, of course.
In some sense, let me just go to I have some bonus slide, which is because I anticipated this question. So you mean the pseudospectral, right? The concept of pseudospectral. Yeah. Okay, so pseudospectral is defined by the matrix norm of the solvent. This is just the Green's function, the matrix norm of it.
Yeah, exactly.
Being larger than 1 over some epsilon. I call it the epsilon tilde because it's not the same epsilon that I have. And the pictures look like this, right? In the complex
yes.
frequency plane. And if I take this the spectral norm, I can derive this equation here, which tells us that this expression here, the nth root of this expression here of the epsilon tilde xi is an upper bound for the spectral radius. It's what's also called. I mean, this is called the pseudospectral radius.
Yeah, exactly.
In this sense, it's this inequality here is the same when we identify the epsilon tilde with epsilon times h1 in the spectral norm of h1.
Yeah,
so
okay.
This sense, it's let's say well known, but my focus is here on this xi.
Yeah, so it's a kind of growth rate in the vicinity of the exceptional point, how the energies are influencing this spectral landscape in a certain sense.
Yeah, you can. Yeah, I think you can say it this way. Yeah.
Yeah. Okay. Thank you. So you are well aware of these interrelations of these techniques.
Yeah. I was thinking put it also in my talk directly, but I thought it's maybe distracting from the thing. But it was clear somehow that the question comes. So it is strongly related, right? And it's but my focus is on the associating a number to the exceptional point. Usually you do not do this when you look at the pseudospectrum.
Yeah, sure, yeah. Okay.
Pseudospectrum somehow serves a different purpose, but it's
yeah. Okay, thank you.
Okay, yeah, it was indeed a very good question. Let me jump back. Okay, so what we see at this numerics, we see first of all, I mean, this inequality is valid, or is fulfilled, because x is never larger than 1. And we see also that the numerics indicates that the boundary is sharp, meaning that you can reach 1. I mean, at least approximately, right? There's not a big gap or something like this. Okay. Here is now for passive systems, I do a similar calculation. I take even more realizations, 100 times more, and I select those realizations that have a positive semi-definite decay operator. And consider only those. Yeah, then I have random exceptional points in passive systems. To have a crude estimate on the closeness for gamma being a rank 1 matrix, I have just defined this quantity. It's the largest eigenvalue of gamma divided by the second largest one. So if this quantity is very large, it means that gamma is close to a rank 1 matrix. Yeah? Now I do the same calculations. I calculate psi, the upper bound. I calculate this r just for representation reasons. I take the logarithm, and then I have the probability density. So what we see first, we see that this psi is never larger than the boundary, yeah, which just kind of numerical confirmation of the equations I have or inequalities I have shown you. What we can also see is that the psi approaches its maximum values when r becomes large, yeah, indicating that when gamma becomes a ring one matrix, this upper bound becomes maximum. What we also see is that the bound is not sharp because psi divided by this upper bound psi up is smaller than 1, much smaller, considerably smaller, right? So that means, it does not mean that the bound that I calculated, so this is for an exceptional point of order 3, and maybe forgot to mention, 10 to the 9 realizations. So it does not mean that the bound is wrong, right? It does mean it could be better, yeah? So it's just not a very sharp point. Okay, I come back to this in a second. Let me just have a small drink of water. I just recovered from Corona. I have a bit throaty, a little bit pain still in the throat. Okay, now what I mean, now I want to look at the distance between a given exceptional point and a set of diabolic points. And let me explain what it means with this. So what I mean is that I look at not at the distance of exceptional points and diabolic points, but between the Hamiltonians corresponding to these situations. Yeah. So I define a distance function in this very natural way. It's just saying distance between matrix A and B is the matrix norm of the difference A minus B. Yeah, it's textbook knowledge, of course, that such a distance, that this is really a distance or a metric because it fulfills these 3 properties because of the properties of the metric norms, right? Okay. One simple example is the Frobenius matrix. Distance is just this distance function, and you use the Frobenius norm, and then it's just the natural generalization of the distance between 2 points in vector space, right? It's kind of Pythagoras-like distance in metric space. Yeah. Okay, now then we define the distance between exceptional point of order n and a diabolic point of the same order n by using the Hamiltonians. We are in n, we have Hamiltonians of size n times n, both for the Hamiltonian at the exceptional point and also for the Hamiltonian at the diabolic point. The Hamiltonian for the diabolic point we can always write in this simple manner. It's the eigenvalue at the diabolic time times the identity. Right? This is always true in any orthonormal basis that we can now choose. Okay, then we write down the distance between the given EP and the given DP. We can write this way. And then now we ask the question, what is the minimum distance? So when I vary now the eigenvalue of the diabolic point. Yeah. So this is then the distance between the given exceptional point and the set of diabolic points in metric space. You are, I guess, familiar that there are these matrix nearness problems. This is now another matrix nearness problem. There's a very nice review on the history of these matrix nearness problems. For instance, you can ask the question, what is the distance of a given non-normal matrix to the set of normal matrices? Or what is the distance to, and what is the minimizing matrix then, right? And you can also ask, what is the distance between your matrix and a matrix with at least 2 equal eigenvalues, something like this. This actually, latter is a rather complicated question. Our question is obviously related, right? But it's actually simpler, much simpler. Okay, we can write it down. So first of all, we will displace our Hamiltonian at the exceptional point by this traceless part, n. Yeah, just very simple rewritten. Then we take the Frobenius norm. Yeah. Yeah, why not the spectral norm? If you can do it with the spectral norm, please let me know. That's somehow very complicated, but the Frobenius norm fits very well, and also the results can be used quite conveniently. So we take the Frobenius norm, and we take advantage of the fact that we can write the Frobenius form also by using the Frobenius inner product, right? And then we we see, it's easy to see that the Frobenius inner product of the identity with the identity is just n. Yeah? N is the dimension of our Hilbert space. The scalar plot of n with n is nothing else than the trace of n, and this is 0 because n is a nilpotent matrix. Yeah, the trace of any nilpotent matrix is 0, and the same for this scalar product. If you use these equations, then we can use with the Frobenius inner product, we can write this distance here. I have squared it. Here it's simpler. We get just these two terms. And then, of course, you directly see, oh, this expression is minimal if the eigenvalue of the diapolic point equals the eigenvalue of the exception point. Yeah? So this is then also the unique minimizing Hamiltonian at the diapolic point. And then if this is here 0, we take the square root and we get a simple result that this distance between a given exceptional point and the set of diabolic point for the same order n is the simple expression here. It's just the Frobenius norm of our matrix n. Yeah, very simple. Okay, normally you ask, okay, nice simple formula, but what is it useful for? And it can be used for two different things. The first is we can relate it to the spectral response strengths. This kind of looks first a bit trivial. So this is the distance that we have just calculated. This is the spectral response strength, and the only difference is the exponent. And this difference, of course, disappears if n is 2. So for an exceptional point of order 2, these two quantities are just the same. Okay, now more interesting is, of course, n larger than 2. Now what we could, then the quantities are very different, right? But we can relate them. So one possibility would use this sub-multiplicativity, relating this or writing down this inequality. And this you can directly then use, this is here the xi, and this is the distance delta, and you get an upper bound for the spectral response strengths. This is possible, but actually it turns out that this upper bound is very poor. It's not sharp at all. One can do much better, just technical detail, but it's nevertheless somehow funny. So it's known that for nilpotent matrices, yeah, and n is nilpotent, when the index is larger than 2, one can write down inequality of this type. And this is much better than that type, because the prefactor here is larger, sorry, it's smaller than 1. Yeah. Forget about all the details. If you use the proper values here, the k being n minus 1, then we get finally this inequality, this prefactor. This is well below 1. So this is a better formula than that one. But in principle, we use it now the same way. We say, oh, left-hand side, that is my spectral response strength. The right-hand side, this matrix norm here is the distance that we have introduced. This gives us this equation here. And now the physical meaning is the following. If I know that my given exceptional point is close to the set of diabolic points, and the delta is small, it means necessarily that also the psi is small. So this exceptional point will be weak in the sense of spectral response. And if the delta, the distance is large, then potentially this inequality tells me the response of this exceptional point can be large. Yeah? And this had actually important consequences. It's possible to know that often, maybe often is too much, but sometimes people fabricate an exceptional point by starting with a diabolic point. Yeah, for instance, when you have a periodic system with a band structure and you have a Dirac point, yeah, there's nothing else than a diabolic point. So people start there, now add a little bit dissipation, and then they can turn this diabolic point into an exceptional point. Well, in K-spaces can also be a ring of exceptional points, but it's actually one exception point. Now, my statement is, if you do this and use only a small perturbation of the diabolic point, a small dissipation in this case, then necessarily your exceptional point will be weak. So potentially not useful for any, let's say, sensor application where you want to have a large splitting for a given perturbation. Yeah, this is some important consequence. I also come to an example in a second once again. Another consequence is if you take an exceptional point and vary the parameters of your system and you approach a diabolic point, that means that the distance becomes zero, approaches zero. And this, with this inequality, tells you, the spectral response thing must also be zero. So in this sense, a diabolic point is an exceptional point with zero response strengths. Okay, before I come to the example, let me also mention, once again, passive systems. I mentioned that the decay operator is positive semi-definite. We use this property now not to derive an inequality for the spectral response strength, but first for the distance, and we find this inequality. Now with this inequality, we plug it into this inequality, and we get this inequality. Now this is now the upper bound for the spectral response strengths for passive systems for all arbitrary n, right? Again, this 2-time absolute value of imaginary part of EP is the line. Now let us compare this with the results I have shown you a few minutes ago. For n equal 2, we get exactly the same result. Now for n equal 3, we don't get exactly the same result. We get a smaller result. So the prefactor here is 6. Before it was 2 times square root of 3, which is about 7. So it means it gives a better bound, than we had before. We can also check that the numerics I have shown to you is also consistent with this. It's still not the sharpest bound that you can have, but it's sharper bound. And the third point is that this equation now is really valid for all dimensions. Okay, now let's come to one example. Now let's come back to this microdisk problem. So we have a microdisk. Now let's assume we have a situation where we have 2 modes in a perfect ideal microdisk, so circular shaped, with similar frequencies. I call it frequency is x1, x2. This is some kind of dimensionless frequency. Just use some scaling. R is the radius, omega the frequency, c is the speed of light in vacuum. Let's assume we have this situation. We come to this situation, for instance, by just looking for some mode pair where this occasionally happens, or we fine-tune the refractive index. One can also do this experimentally in certain limits. When we have this situation, we can say we are close to a diabolic point, right? We're not perfectly to a diabolic point, but close to. Now, in this situation, when when these frequencies are nearly degenerate, we can use a perturbation theory for weak boundary deformations. Weak boundary deformation means we take our disk with radius r and add a small boundary modulation. So f of phi and f is small. And I don't want to show the formulas, this would be another talk. The final result is, if I take this for these 2 modes, I end up with a 2x2 Hamiltonian. It looks like this. X1 and x2 again are the frequencies, complex frequencies. The A's are the Fourier harmonics of your deformation function. So if you know the deformation functions, you know all the matrix elements. It still is just 2x2 matrix, but it's somehow nevertheless remarkable, because when people in optics write down 2x2 matrix to describe their physical systems, they usually use coupled mode theory in the spirit of I have a mode in this cavity, I have a mode in this cavity. They are for sure somehow coupled. So I spend a coupling element, and maybe later I try to compare with experiment, and I have to somehow fit it to the experiment. Here, now given the deformation of the cavity, I can write down everything explicit, right? Of course, if you have everything explicit, we can of course do all the calculations that we mentioned in this talk. So first of all, let us take a bit slightly more concrete. Let's take this example here. So I forgot to mention that m is the angular momentum number. So the number half of the maxima that you see. It's the angular momentum number. It's the mode number of the orbital angular momentum. Here is just 18. The radial mode number here is 1. That one is 2. Or 0 and 1, depends on your own count. So what we want to do is we want to couple modes with different angular momentum. Okay, so we take this example, we choose the refractive index 2.1, And then we choose this boundary deformation function. Yeah, it's not, if you look at the equation to see it, it's not obvious, but it takes a half an hour maybe to see it. This gives us two deformation functions, and now we can do everything explicit. We can calculate the critical values of these deformation parameters, which give us an exceptional point of order 2. Everything is explicit, but only important is the following fact that the numbers that comes out are small. Yeah, 10 to the power of -5. That means that the deformation is really, really tiny. So if you look at the mode here, and I hope you can see the boundary. Yeah, it's not a circle. It's a circle plus a very weak deformation. You cannot see the deformation. Yeah. Now, the people working with microcavities, when you tell them, weak deformation is sufficient to make an exceptional point, they say, oh, great, because usually a strong deformation spoils the quality factors, so spoils the long photon lifetimes in the cavity. So here you can say, okay, potentially you stay with large quality factor. Yeah? This is, by the way, the mode at the exceptional point, the single mode exceptional point. Just for a comparison with numerics, so here we have plotted the frequency, here the imaginary part of the frequency, here the parameters epsilon. Sigma is fixed to this value, and you see, first of all, you see the square root behavior here, the exceptional point. By the way, PT, I'm very sorry, PT means perturbation theory. It's a kind of running gag. BEM means boundary element method. That's one numerical scheme to solve the full two-dimensional, in this case, two-dimensional mode equation. And we see that's a very good agreement. So the theory, the perturbation theory works very well. Now, if we now do the machinery with the response strengths and the distance, we get this simple result here. So first of all, the response strengths and the distance are the same because this is an exceptional point of order 2. And the result is this simple result. So x1 is the frequency of one of the modes, is the one with the largest Q factor, of the larger Q factor, let's say. A and P is the Fourier harmonics that couples the two modes. Yeah? And what we see is, since A is small, yeah, the deformation is small, this distance and also the response strength is small. And it means that it's true that the weak deformation of a microdisc can lead to an exceptional point of high quality factor, but it then necessarily has a weak spectral response. So not of use for any exceptional point based sensor, for instance. Unfortunately. Okay, so with this, I would like to come to a summary. So I have addressed the question of how strong an exceptional point is. So in the sense of spectral response strength, psi, this quantity that gives you the splitting or an upper bound for the splitting of the eigenvalues, the change of the eigenvalues under a perturbation, and also the intensity response to harmonic excitations. The eigenstate response, then zeta, gives you the change of the eigenvectors under a perturbation of the system. Then I've introduced the concept of the distance between EP or given EP and the set of diabolic points. And this distance gives you an upper bound for psi. And for passive systems, both psi and delta are bounded from above, which is a severe restriction for passive systems. And this cartoon you can read for yourself. Don't take it so seriously. Now, the take-home message is that the response of an open system at an exceptional point of order n can be quantified by a few, and I have to say easy to compute numbers, which are helpful for the design of non-Hermitian systems for EP-based applications. With this, I would like to thank you for your attention.
Thank you very much, Jan. Thank you. Questions, comments? Philip has a question.
Yeah, well, first of all, thank you for the presentation. I have a very small question. You mentioned earlier on the relationship of exceptional points to normal matrices. Now, if a matrix has an exceptional point, then the upper triangular form and the lower triangular form don't commute. So it's clearly not normal. Yes. But is there a converse? Is there a statement that says if a matrix is not normal, it must have an exceptional point, or is it just one way?
It's just one way. Because you can have a matrix which is non-normal, but there is no exceptional point.
Yes, that's what I didn't have enough time to try to construct an example. So it
Yeah,
really
for
is,
instance,
it really
yeah,
is just if a matrix has an exceptional point, if you can put it in the Jordan canonical form, it will not be normal.
A normal matrix
Yes.
is almost by definition diagonalizable.
Yes, but
Yes.
there's no rule which says that a non-normal matrix is not. That's what I'm
Yes.
asking.
Yes. For instance, let me just, this most simple example is this one here. This is obviously non-normal and it's an exceptional point.
Yes, that's clear.
Imagine instead of a B, take a 0, take a B.
Oh,
B
well,
different from A. Then
Yes.
this is non-normal in general. But
it's
not
still
an
non-normal,
exceptional
but
point.
it's not exceptional. Very good.
Yeah.
Okay.
Federico.
Yes. So first, thank you also for the very nice talk. So I have a question. So in the first part, when you were describing the strength of the exceptional point to perturbation, if I understand correctly, the really relies you have a action of the expansion of the Green's function, right?
Yes.
And so, but this truncation depends on the fact that this matrix N is nilpotent. So
Yes.
I was wondering, so if you have an exceptional point, then of course it's nilpotent. But is it true also the other way around? So can you have a nilpotent matrix also with other eigenvalues which are not exceptional points?
Okay.
So can the
question
expansion truncate for other? That's the question.
Yeah. So if you have an n by n matrix, and if this is at nilpotent with the same index, then it's necessarily an exceptional point of order n. I would guess that maybe I not fully understood the question because the quality was not very. The transmission was not so clear, not so good. If the question was also if the Green's function looks like this, is this always an exceptional point? I would say yes, but I'm not 100% sure.
Yeah, because the argument, as far as I understand, depends on the fact that this expansion truncates, and this depends on the fact that the matrix is nilpotent. And then the observation is if you have an exceptional point, it is nilpotent. But I was wondering if it's also the other way around.
I think, yeah, you're right. So it depends really, it's truncated because of the nilpotency. And if it's nilpotent, then it's an exceptional point. So it means if it looks like this, it must be an exceptional point. So you answered your question in some sense by yourself.
And I have another question.
Yeah.
So at some point you showed this spectral response to the X. So
I think you have to repeat the beginning. I haven't understood anything.
So at some point you showed this probability distribution for the spectral response, this variable that you called X.
Yes.
Maybe I didn't get it when you were saying it, but why is this distribution like tilted towards 1? Is it just because of the parameters you chose, or maybe it can be tilted towards 0? Or why is it this shape? This is my question.
Okay, I cannot give you a precise equation for the shape, but the fact it has a little bit to do with the way I show it. I mean, I could also, this bit arbitrary to define this quantity x, right? I could also define a quantity x tilde, which is x to the power of n. Yeah, I could do this. It still would be a quantity which, because of this integral quality, would be between 0 and 1. And if you do this, it looks a bit more symmetric. It's more tilted to the left, let's say. Maybe I'm sure you find some power which gives you something symmetric.
Maybe a simpler question would be, what is the distribution of Q and what is the distribution of H1? You said that these are random matrices.
Yes.
Okay. How do you pick them?
Yeah, okay. This is, of course, an important question. So what I have done is the simplest thing. I took just, for each matrix element, I took just a uniform distribution between minus and half and plus.
Independent for each element.
Independent for each element.
Okay.
Yeah. It's for sure. If you take another distribution, you could, for instance, instead of a uniform distribution for each element, you take some Gaussian distribution, things like this. Then I think the shape of this histogram will look different, slightly different. Yeah. So I do not claim that this shape is here somehow universal. I'm only saying that it's kind of numerical confirmation that this inequality here is correct.
Yeah, but let's say if you just took Q to be the unit matrix and just plays with H1, what would be the result?
That would mean that you are just at a fixed exceptional point.
Yeah, but you are always at if Q is just allowed to go through GLN arbitrarily, I mean, like R measure, this means that you are keeping the exceptional point structure because you don't change the Jordan form.
Yeah, but let me one thing emphasize. When you I make here a similarity transformation, right?
Yes.
And a similarity transformation does not preserve the response strengths. Only if the matrix is unitary. This seems like to be a bug, but it's actually a feature. Because I mean, similarity transformation is what preserving, it's preserving the eigenvalues, right? But all the other interesting structure, like the non-orthogonality and stuff like this is changed. And now the spectral response strength depends on all these internal structure. So if you would write down a quantity which is invariant under self-similar transformation, I would guess that it contains no interesting physics anymore.
Yeah.
So this is an essential feature of this H1 that it's not preserved under a general similarity transformation.
Yeah, but which is more responsible to the distribution, H1 or Q? That's the question.
So I would think that, of course, when I do it with fixed H1, I would think it looks similar. But I have to admit, I have not looked at it because I always varied everything together.
Okay.
But okay, I can check, of course.
Okay. Thank you.
Not yet.
Sorry, Federico, for hogging your question. Sorry.
Uwe.
No, actually, thanks.
Yeah, there's a small comment concerning Joshua's remark and also your answer, Jan. Did you try to relate your technique to this well-known technique by Arnold, this Wiersig deformations? Because he is giving a kind of minimal distance how to perturb Jordan blocks or arrangements of Jordan blocks in order to get maximal output, Wiersig deformations. So it will also include all this direction in metric space where you will have the most efficient deformations. Did you try to relate this to this technique?
What means output and what means deformations in this context?
No, it's very simple. Arnold in the 70s, he was considering all this singularity stuff.
Yeah.
And Jordan blocks, how to deform Jordan blocks, and what kind of and you have additional structure hidden there. So you will have similarity transformations to some matrices will obey some additional symmetry constraints, but they will be similar to Jordan blocks. And you may deform these things by some perturbation theory. And you can see in this parameter space of all these matrices, you have kind of directions where this perturbation is most efficiently and other directions which are less efficient. And he was qualifying these things by group theory and Lie algebra theory, and you get very efficient tools. I was just wondering, did you try to use this or to combine these things? Because in this case, you will probably get all these things without random matrix theory and so on, and you will get it directly. It was just a question.
Yeah, okay. No, I haven't done this, but it's a good point. I will check this. But let me say once again, I'm not really using random matrix theory. I'm just using it as a numerical tool to check the theoretical results.
Yeah, sure. Yes.
Yeah. Okay, a good point. I will check this.
Okay.
I have a general question. bounds, there's always a problem. One can find a bound, but to know how good the bound is, that's a more difficult question.
Yes.
At one point, you showed us how to improve it, but you said, "Oh, but this is not the sharpest bound we can have." Yeah. So,
okay.
So do you have an idea about you have several bounds, about the quality of your bounds?
Yeah. So when I said we can have better, we should have, or I said we can have better ones, right? Or should be better ones. I actually refer to this kind of results. So here I use random matrices again, right? And I think I cover everything because everything is random, let's say, yeah? So I think what I get numerically here, this should be the best bound. Yeah, it's about 1 over square root of 3. Yeah, so if and this is 0.572 roughly. Yeah, so this is what I would expect my theory should give me, right? But the best I found was something with a factor of 6, 0. Sorry, it's not. Okay, so the first bound gave me the not so good bound gave me something like 1, and the other one gives a slightly smaller bound between this value and 1. Yeah, I think 0.7 or something. So I don't have any theoretical tools to tell me what a good bound is. I actually don't know how to do this. Maybe I am too much physicist and not a mathematician. I just refer to the numerical results.
Okay. Thank you. That's good.
Okay. Yeah.
Any more questions, comments?
Jan, Lee here. I have a question regarding your last example. I somehow didn't get the message in the end. I saw the construction of exceptional point, but in the end, how strong is the perturbation?
Here?
Or the response, rather.
Here or the final equation here?
Yeah, so here, yeah.
Yeah, I've seen you came a bit later to the talk. You want to have values, I mean, numbers, or, I mean, the point is that these, I mean, okay, the perturbation parameters here, they are of the order of 10 to the minus 5, right? And these perturbation parameters are essentially what enters, I mean, you're familiar with the perturbation theory.
Sure, yeah.
These values enter here are these coefficients, these full harmonics. They're about 10 to the power of minus 5. So really small numbers. I mean, of course, you have to compare with what, but in principle, you have really small numbers here. So that means that these perturbations, that these response strengths is also small. I mean, you can play around with parameters, maybe try to make it a bit bigger, but you always have the struggle of when you increase the deformation, you lose your quality factor, right? At some point.
Well, not necessarily so, right? So if you perturb it in the right way.
Yeah, okay, but yeah, the typical behavior is like this, let's say, right?
Yeah. You know, what I'm curious is, so for here, so if I want to show that at this exceptional point, my sensitivity to some certain perturbation is strong or weak. So what would you use as an example to show that? So for example, are you going to change the index refraction, or are you going to deform the cavity in random fashion? So how do you imagine that can be demonstrated?
I mean, the central equation is, of course, or the inequality is no, not quite. No, sorry. Yeah, so this here is the important equation. It tells you how the eigenvalues change when you perturb the system with the perturbation H1. And the spectral response side tells you how big this is in general. Now, if you want me to experimentally determine the psi for this particular system, I would say, okay, what you have to do is, first of all, you have to implement your exceptional point by a weak deformation, and then you have to perturb the system in very different ways, in several ways, let's say in 100 different ways. You have somehow to make sure that this prefactor is always the same. Yeah, this is the difficult part, I think. And then you always record the change of the eigenvalues to the power of n, and you take the maximum value using your 100 experiments. And this should give you approximation of the psi. So you have to do many realization, because this is not an equality, it's an inequality, and you only if you assume that the bound is sharp, and then the maximum value of this in many experiments can give you the psi, with the additional difficulty that you have to somehow make this prefactor, keep it somehow constant.
Okay, so is this somehow related to some people's claim that, so even though exception point seems to be more sensitive in the spectral response, but somehow you need to integrate it for a longer time to average the noise? Is it somehow related?
You mean there is some noise in the measurement,
Yeah.
something is fluctuating, maybe these two nanofiber tips in the Lang-Yang experiment,
Right.
that there are some are fluctuating.
Yeah.
That's a good question. So I'm not sure if this is really a good example. Maybe it's a good example. I have to think about this. I have no good answer to this, but it's an interesting question. Yeah.
Thank you for the talk anyway.
Yeah. Okay. Thank you for this question.
I think we should close here. People are leaving now. Thank you very much again, Jan. Thank you for the nice talk. Thank you.
Okay. Yeah. Thanks for the
So
audience.